In this video we're going to be looking at addition polymers. So you probably have heard this term before. Polymers are most commonly referred to as plastics. Okay, it's the most common example of a polymer. And we're talking about addition polymers, but unless we're doing triple, we won't actually need to talk about any other type of polymer. So anyone doing combined science, we only need to worry about addition polymers. So to begin with, we're going to look at the actual sort of terminology that's used. Polymer, monomer. And if we're able to break down what these words actually mean, then it's going to be much easier to remember them. So monomer starts with mono, which means one. If you think about monorail, monocle, these things refer to one. And mer here comes from the Greek meros, which means parts. So when we're saying mono, meaning one, and mer, meaning part, we're saying one part. Poly means many. And mer still means part. So that's all it is. A monomer is one part and a polymer is many parts. So before we get into the specifics of addition polymers, sort of in general, all a monomer is a small, simple molecule. Okay, so here they are. So these are individual monomer molecules. And when they become a polymer, all that happens is that they join in to one long chain. Rather than being individual monomer molecules, they join up into one very, very large molecule. So we have a large polymer molecule. So, as you'd expect, you're going to get very different properties. So our monomers are usually gases, to be honest, quite flammable perhaps. But if we look at polymers and we think about most plastics, I mean, if we just look at the front cover of your student pack, this is a polymer. Okay, this is polythene. Now, ethene is a colorless flammable gas, but polyethylene is very clearly not a gas. It's a solid. It's transparent, and it has very, very different properties. And that's because as a monomer, you've got very small individual molecules, but as a polymer, you've got one very large molecule. And because of that, it changes its properties. I mean, we should remember that the larger the molecule, the higher the boiling point, and the more viscous it becomes. So it should be no surprise that when we take these smaller molecules and join them together into one larger molecule, they are going to have much higher boiling points and even melting points. So if this is a gas, this is quite likely to be a solid. And these joins between them, these are covalent bonds. So our individual monomer molecules join together into this large polymer molecule. Now we need to apply that principle to organic chemistry. So to make addition polymers, you must have an alkene to start with. Okay, so you must have an alkene. It's not possible for alkanes to become polymers. It needs to be an alkene because the alkene has a double bond. Okay, and that is crucial for its ability to join up into this polymer chain. So as I say, create a flow map explaining how polyethylene is made from ethene molecules. So we'll start with ethene. So we've got 2 carbons because it's eth. So 2 carbons. It ends in ene, so we know it's an alkene. So we're going to give it a double bond, and then we're going to make sure that each carbon has 4 bonds. It's already got 2, so it only needs 2 more. So that's ethene. And the reason why it's able to join up into a polymer, to start with, at the moment there's no free bonds. The hydrogens can all make 1 bond, and they have. The carbons can all make 4, and they have. But what can happen, just like with the alkene reacted with the bromine water, what's able to happen is it's able to break that double bond. And if it breaks that double bond, well then suddenly this carbon has a spare bond and this carbon has a spare bond, and then they can join up into a polymer. So the first thing that must happen is the double bond must break. So the double bond in the alkene monomer breaks. Right, that is step 1. And once that happens, it's able to join up with neighbouring alkene molecules. So if I had an alkene, so if I had my ethene here and it's broken the double bond, okay, so I've broken the double bond, and now it can form bonds either side. So the monomer can now form bonds to other monomers. And then what's going to happen is they're going to join up into a chain. So lots of different ethene molecules are all going to join up into a long chain. Now the problem with this is it's not going to be 1, 2, 3 or even 100 molecules that join up into this chain. It's going to be huge numbers, okay? So the monomers join together to form a large, very large polymer chain. Okay, so alkenes are the only organic molecules that are able to do this, and they do that by breaking the double bond, which allows them to form these 2 new bonds. We call these continuation bonds, and then they join up into a large molecule. Now I'm only showing here, this is a small section, okay? Physically didn't have space to draw the whole molecule, and even if I had A3 paper, A1 paper, I wouldn't have enough space. So this is just a small section. Because it is a giant molecule, enormous molecule, so just a small section that I've drawn here. So what we can do then is it's not reasonable. It's not reasonable to even draw a section like that. That's still too big. We couldn't possibly draw the whole thing. So we can, I'm going to show you how we're going to draw them. So to start with, I just want to sort of recap, how we draw hydrocarbons, making sure that we get them right, and then how do we turn them into polymers? How do we draw the polymer? If they're so big and they're so massive you couldn't possibly draw the whole thing, how are we going to represent them? So we're going to start with ethane. Now notice it's ethane, so it's an alkane. So eth meaning 2 carbons, ane meaning you keep the single bond, and then each carbon needs 4 bonds in total, so you add your hydrogens. When it comes to ethene, we're going to do the same thing. 2 carbons, because it's eth. It ends in ene, so we're going to add a double bond, and then we're going to give each carbon 4 bonds. Now, when it comes to the polymer, naming the polymer is incredibly simple. You take the name of the monomer, and you put poly in front of it. So ethene becomes polyethene. propene becomes polypropene. Butene becomes polybutene. Think of a polymer that you know commonly, like polystyrene. Well, the monomer to make polystyrene is called styrene. And you don't need to know anything about styrene, but just from its name, styrene, you know it's an alkene. It must contain a double bond. So I'm going to fill this section in last. We're just going to draw the alkanes and alkenes to start with. So propane, prop, so that's 3. So 1, 2, 3 carbons, and it ends in ane. So I'm going to keep these as single bonds, and then I'm going to make sure each carbon has 4 bonds and put my hydrogens on the ends of those bonds. Propene, again prop, 3 carbons, 1, 2, 3, ends in ene, so I'm going to add a double bond. It doesn't matter where you put it, so I'm going to put it here. Make sure each carbon has 4 bonds. And then butane, but, so that's 4, 1, 2, 3, 4, ends in ane, so I'm going to keep these as single bonds and add my hydrogens so that each carbon has 4 bonds. And then butene, again but, so that's 1, 2, 3, 4 carbons, ends in ene, so we need to add a double bond. Again, for the purposes of this exercise, it doesn't matter where you put it, so I'm just going to stick it here. And then make sure each carbon has 4 bonds. And then finally, pentane, pent 5, 1, 2, 3, 4, 5, ends in ane, so I'm going to keep all of these as single bonds, and I'm going to add all of my hydrogens again to make sure every carbon has 4 bonds. Because carbon has 4 outer shell electrons, it can form 4 covalent bonds. Don't know what was going on there. And then pentene, again pent, 1, 2, 3, 4, 5, ends in ene, must have a double bond. I'm going to put it there. Make sure each carbon has 4 bonds. And what you'll see, every single one of these in the first column is an alkane. Every single one of them will follow this general formula. They will have twice as many hydrogens as carbons plus 2. All of these are alkenes and they will all follow this general formula, CnH2n. Very similar to the general formula of the alkanes, only you don't have that plus 2. Because when you have a double bond, you lose 2 hydrogens. So you don't need that plus 2. So, drawing them as polymers. Now, every polymer, every addition polymer has the same basic structure, okay? Because they all come from alkenes, it means they've all had to have a carbon-carbon double bond. And that carbon-carbon double bond must break. In order for it to become a polymer, it must break that carbon-carbon double bond. So you're always going to draw 2 carbons with a single bond, and they represent the 2 carbons that used to have a double bond but is now broken. Okay? You're then going to put square brackets around the whole thing, and you're going to draw 2 bonds that go through the brackets, not up to the brackets, not outside the brackets, through the brackets. Now this bond here, this is our continuation bond. This represents the bond that our monomer is going to form with the next monomer and then with the next monomer. So what we're doing is we're drawing one repeating unit. We're basically drawing one section, one monomer to represent the polymer. Now obviously we're not looking at one monomer, are we? We're talking about thousands, hundreds of thousands, probably millions. So what we're going to do is if we say, well, if we had n number of ethene monomers, then we would get this pattern repeated n number of times. So there's usually 3 marks for a diagram for an addition polymer, and 2 of the marks are right here done already. 1 mark for the single bond, because obviously it used to have a double bond, but it's now broken, so we've got our single bond there now. And the second mark is for the continuation bonds and N. Now, if I wanted to draw polypropene, you would think that would be very different, but actually our starting point is exactly the same. 2 carbons with a single bond, square brackets, continuation bond, N. Because even though propene has 3 carbons, this diagram is only representing the 2 carbons that had the double bond. So we're only actually showing these 2 carbons here. Now this carbon hasn't disappeared, we're going to talk about it in a minute. But you're only drawing the 2 carbons with the double bond over here. And obviously it's got a single bond now because that double bond has broken. So polybutene, no prizes for guessing what this is going to start off as. 2 carbons with a single bond, square brackets, continuation bond, N. So if I had N number of butene monomers, I would get this repeating N numbers of times. Again, butene has 4 carbons, but I've only drawn 2 because I'm only drawing the 2 that had the double bond. And then finally, for pentene, 2 carbons, single bond, continuation bonds, N. So, this is where they start to differ from each other. So, we know that these 2 carbons were the carbons that had the double bond. So this carbon here is this one, and this carbon here is this one. So, just look at what's bonded to it. This first carbon had a hydrogen and a hydrogen. So we need to give this one a hydrogen and a hydrogen. This carbon is here, and that one has a hydrogen and a hydrogen. So we give it the same. There we go. That's ethene, that's polyethene. Let's look at polypropene. This first carbon here is this carbon, which has a hydrogen and a hydrogen. So we'll give it its hydrogens, same as it had as a monomer. And this carbon is here, and it has a hydrogen and a carbon. And that carbon has 3 hydrogens on it. Now I could have gone up. I could have put the hydrogen down and the carbon up. It wouldn't have mattered. Either one's fine. So this is polypropene, and you can see all 3 carbons are now there. Let's look at butene. This carbon is this one here. It's got a hydrogen and another hydrogen. This carbon is here. It's got a hydrogen, but it's also bonded to a carbon, which is bonded to another carbon. And you can draw the hydrogens that they're attached to. And there we have polybutene. And then finally, polypentene. This carbon is this carbon here, so it's got 2 hydrogens. And this carbon has a hydrogen, and it's bonded to a carbon, which is bonded to another carbon, which is bonded to another carbon. So I can just put them down here. And there we go. So they all started out the same, but they have ended up being different. But remember, there's 3 marks available. So even if you just remember the carbon-carbon single bond, the square brackets, the continuation bond N, then you've already got 2 of the marks, even if you do make a mistake and mess up the rest of the bonds. But this should be, as long as you follow the sort of the pattern and the rules, it should be nice and easy. And most of it will already be drawn for you. They tend to give you the carbons and the hydrogens, they just haven't given you the bonds. So you just got to remember how many bonds and whether they're singles or doubles. So, once you've done that, if you could just turn the page, there's another progress check. Okay, so there's progress check here, and it carries on here for a few more pages, goes to page 133. Again, a mark scheme will be coming out in due course. So for now, if you could just answer it, it's all multiple choice, most of it at least, and then when you get the mark scheme, we can arrange for you to submit your scores on Show My Homework.